Let's look in a little more detail of the internal structure and behavior of processes. I want to start by looking at the process lifecycle, and I'm just going to show another little timeline here with these cartoon representations of processes. Got a parent process here that came into existence previously, and we'll see basically how that could have happened here in this little diagram. In order to create a new process, an existing process needs to run a system call called fork. After the fork call, there's now two processes, the parent and then the child, and they're essentially copies of each other. The fork call doesn't create a new running program, it just duplicates itself and creates a process that's running the same program that is running in the parent. If the child wants to run a different program inside the process, it can then run another system call called exec, and that's going to replace the program that's running in the child process with a new program that's loaded off of disk. And I've indicated that switch over by showing the child process in a different color. Now at that point, both the parent process and the child process are continuing to execute. So just to illustrate that, I'm going to have the parent process and the child process kind of alternate back and forth a few times. At some point, the child process terminates, which I'm showing here with the squared off end to its timeline. One controlled way for the child process to terminate is to run the exit system call, at which point it becomes what's known as a zombie process, and we'll talk about that some more. The parent process can also optionally wait for a child process to terminate so that it can, for example, retrieve values that were created by the child process or do other lifecycle processing going forward. In order to do that, it runs another system call that's called wait. At that point, the zombie process, which represents kind of the remnants of the execution of the child process, can be discarded by the kernel, and the information that was left behind by the child process can be retrieved by the parent, which then continues to execute. So you can see here we've basically got the entire life cycle of the child process. At some point in the past, a process had been started, which then does a fork. The child process will do an exec to run a different program if that's what it's supposed to be doing. When it's done doing its thing, it'll exit, resulting in a zombie process that can then be collected by the wait system call in the parent, and that completes the life cycle of the process. One thing that's really important in this discussion of how processes work is the idea of a process ID. So this is a unique numeric value that's assigned by the kernel when a new process gets created. So when that fork system call gets run by a parent process, the child process is going to get a new process ID. And you can actually access that inside of your program by using the C library called getPID or getPID, some people say. It's just process ID. That gives you the process ID of your current process. Because you were created by some parent process, you also have access to the process ID of your parent, which you can access using this library function getPPID or parent process ID. These process IDs, again, are going to be really important when we think about how those system calls work. Let's look at these various system calls in more detail. We'll start with the fork system call, which you recall creates a new child process. And just for your reference, I've included down here at the bottom of the slide that same cartoon for your reference. As we saw previously, the parent is going to create a new child process by invoking the fork system call. And just like with the example we talked about before with the write system call, what's going to happen is that parent process is going to basically create a trap into the kernel that's going to run this fork command that will create a new process and return back to the caller when the process has been created. Remember that both the parent and the child process are executing the same program to start with. So what is unusual about this is that essentially the parent calls that fork system call one time, but it actually returns in both the parent and the child process. The child process is essentially identical to the parent, including the location where it's executing. So the instruction that gets restarted after that trap is completed is going to be the same instruction in the parent and in the child. Normally you want to have the parent and the child do different things following this fork system call, so the two have to have some way of distinguishing one from the other because they otherwise look identical. They need to be able to check, am I the parent or am I the child? The way that that's supported by the fork process is that in the child, the fork is going to return a 0. And in the parent, the fork is going to return the process ID of the child, which the parent could use later on to wait for the completion of that child process. It's important to note that 0 is not a valid process ID. The process IDs all are positive values. The smallest one is the process ID 1, which is the init process that I alluded to in the last talk. So the fact that this function gets called once in the parent but returns twice, once in the parent process and once in the child process, is what leads to the necessity of this convention of saying we're going to give back a 0 in the child and a non-zero process ID in the parent. That allows us to write code that will do different things based on whether we were running in the parent or in the child. I've been saying that the child is almost completely identical to the parent. It starts out with a complete copy of the virtual address space of the parent. It inherits all of the parent's open file descriptors, so standard in, standard out, standard error, and any other files, network connections that the parent might have open. A key distinguishing characteristic, again, is that it's got a different process ID. So the parent is informed of the process ID of the child, but the parent has itself a different process ID. And if the child wants to learn what its process ID is, it doesn't get that back from the fork call, because that would make it ambiguous, determining whether it was the parent or the child, but it can still make a call to that get PID library function that we just looked at. We're basically at this spot in the cartoon. The fork took place, it returned in the child, and the child can figure out that it was the child by looking for a 0 return value. It also returned in the parent and allowed it to continue to execute going forward. Here's an example of doing this in C. So here's our little main function. We're going to define a process ID variable, and PID_T is a standard library type, and we're using the _T suffix as an indication that that's a type def. It's really just an integral value under the hood, but it's good to be specific if we can. And I've defined another local variable called x that we're going to use below. The first thing that happens here is that we run the fork system call. That's going to be executed again by the parent process, but because the parent process will be essentially duplicated in the child process, both the parent and the child will continue executing by returning from this fork system call. And they're both going to store the return value from that fork in this variable called PID. Now what we want to do is do two different things based on whether we're in the parent or in the child. So in the child, we know that the fork call is going to come back with a PID of 0. It's probably a poor name for this because it's not a process ID in that case. But this allows the child to say, hey, I'm the child, and what it's going to do is print child and then a value of x that it's going to pre-increment. So what we'd expect to see here from the child is this string child, and because x was initialized to 1, we're going to increment it to 2 and print 2 as the value for x. And then the child is going to immediately exit. So that's going to terminate the child process. Again, this is a system call, goes out to the kernel, says, I'm done executing, put me out of my misery. On the other hand, if the process ID was not 0, that means that we're in the parent process, and when the fork call returned, we got the process ID of our child. So in that case, we're not going to take this if statement, we're going to run this printf that's going to print parent, and it's going to decrement the value of x, just to illustrate that it's in a separate address space, and then exit. If we compile this program down and call it fork, and run it at our command prompt, we'll see these two lines come out. Parent x equals 0, because it decremented the value of x, and child x equals 2, because it incremented the value of x. Note that this is one possible sequence with which those two outputs can appear. Because they're actually coming from separate processes, we could also have expected to see child x equals 2, and then parent x equals 0. There's not really any synchronization going on here. Whatever order the operating system happened to sequence and schedule these two processes determines the sequence with which those appear in the standard output. So that's the behavior of the fork system call. In some cases, we may just leave things as is after the fork has completed executing. For example, if we've got an HTTP server that's running in some process and it wants to be able to cope with more traffic, one approach to that is to spin up multiple copies of itself. So it could just fork several times and let each of the child processes continue to run the HTTP server program, but now you'd have more capacity to deal with more inbound requests. In a lot of cases, however, we're going to want to run a different program in that child process, and that's the job of the exec system call. The full-on system call is actually referred to as exec VE, but I'm going to just continue to call it exec. If you go look at the man page for these guys, you'll see that there's a whole family of them that have different kinds of arguments and so forth, but this is kind of the most comprehensive version of that. What exec does is it loads a different program into the current process. If the child process wants to run a different program, it will itself run the exec system call, and that asks the operating system to essentially replace the program that's running inside that process with a different program that's been loaded off of disk. It's kind of like the child process is asking the operating system to replace its brain with a totally new one. The arguments that get passed here to execve are the following. First of all, the name of the executable file, so that's the file name parameter, and it's just going to be a file that the kernel can go find out on disk. It could be, for example, an object file, an executable that's compiled code. It could be some sort of a script that has a shebang line as the first line that can invoke an interpreter and run that. Basically anything that you might imagine running from the shell is fair game as the file name to pass into the exec command. And as you wouldn't be surprised to learn, this is exactly the mechanism that the shell uses. When you type the name of a command, it reads that command off of the command line, goes and finds the location of the executable for that command in the file system, and does a fork followed by an execve. You can also pass to the newly executing program in the processor information that's going to be made available in the argv array in the main program. Remember that when you start up a program, it's given information about how many command line arguments it received and what those arguments are, and those are made available to you by declaring those two variables argc and argv by convention in your main function. Where do those come from? Well, it turns out they come from whatever the parent process passes in as this second argument to the exec function. Finally, something you might not be familiar with is that when you are writing a C program and you declare those argc, argv values, you can also declare a third parameter there that's usually called env or envp, and that is going to point to an array of strings that correspond to what we commonly call the environment. So when you define an environment variable and make it available to a program inside the shell, the way that that's done at the time that the shell program executes a subordinate command, in order to make those environment variables available to that child program, the shell itself, after it forks and then as it's about to exec, is going to grab those values out of its environment and hand selected ones to the child. Then the child can have access to them using either the declaration on main or some variant of the getenv functions that are available in the standard library. In summary then, what the exec system call does is replace, in whatever process calls it, often a child process immediately after a fork, it's going to replace the code, the data, and the stack from inside that child process with the corresponding elements from the new program that's been loaded from disk. It's going to hang on to its process ID and any open files that were present when it was forked. Some child processes will go ahead and close those open files in order to clean up after themselves, but they're not required to. This is kind of the complement to the fork call in a way. Remember that we said that the fork system call is called once in the parent, and it returns twice, once in the parent and once in the child. The exec system call does kind of the opposite. It's called once, and it never returns, because by the time that the contents of the code and the data and the stack and so forth in the process have been overwritten with a new program, there's nothing to return to. Instead, the kernel will have arranged for the code that was loaded from disk to be executed right from the beginning. Here's a simple example of using fork and execve. This might actually be something quite similar to what the shell would do when it's trying to execute a command. So for example, if at the command line we had typed in /bin/ls, that's actually where the ls program lives on disk, and then I've given it a couple of other command line arguments here. The way that the shell might implement that would be as follows. First of all, it's going to want to do a fork because it needs to run this different program, the ls program, instead of running the program that implements the shell, which is what's running in the parent process here. So the parent calls fork, and again, fork returns twice, so the parent is going to go off in a different direction. Here I'm only showing the response in the child process where the PID value returned from fork is 0. The child is then going to just turn right around and call exec VE. And I'm showing some sort of generic arguments here, but we might, for example, pass in /bin/ls as that first argument, because that's actually an executable file that runs the ls command. We've got some additional arguments here that might correspond to these two space-separated values that are going to be passed as argvs to the ls command. And then an environment variable that would reflect the contents of the current environment setup in the shell that is about to run this execve command, and that will also be passed to the ls command. Now I said before that execve is called once and never returns. That's almost always true. The issue might be that if the exec command cannot find this file, if we gave it a bogus name or something had changed on disk, it's possible for execve to actually just fail outright. So if it can't find that thing, it's going to return a value that's negative. And here I'm just showing that we've trapped that case, printed some information out about how we couldn't find that command, and then we just exit the child. And this is, again, probably pretty similar to what a real shell actually does. If you type in a bogus command at the command prompt, then by the time it reaches the point where it's going to try to execute that command, if it doesn't find it, then something's going to go haywire and you're going to get some kind of a message back from the shell that says, hey, sorry, I couldn't find this thing that you asked me to execute. Okay, returning back to our little cartoon diagram here, we can see that after the child is done doing whatever it's going to do, it may call the exit system call. And that's what's illustrated here in this slide that talks about how we terminate a process. So the child process is done doing its thing and it wants to signal back to the kernel that it's completed. So there's several ways to exit a process. One is to call the actual exit function, and I've illustrated that up here. Exit takes as its single argument a status value that's an integer. So you can call that function, and what it's going to do is cause that child process to terminate with some status value. And that status value is available to the parent process, as I mentioned before. When we do a wait in the parent process, we can actually access that. If you've ever used $? in bash, for example, that gives you the exit status of the most recently executed command. So bash also does this. The convention in Unix is that if that status value is 0, that it indicates that the command terminated normally. If it's non-zero, that's an indication that the command terminated abnormally, and the specific non-zero value ideally will give you some information about what went wrong. This is kind of a reflection of the notion that there's only one way for things to work and a lot of ways for things to go wrong. But this provides a helpful way for the parent process to learn what might have happened in the child. You can also, it turns out, when you want to return a particular status value back to the parent, is just return an integer from your main function. If you look at a correct declaration of the main function in a C program, main is always defined to return an int, and that's exactly what's going on here. We can return that integer from main, and the runtime code that wraps up your main program will arrange to send that back to the parent process. You might think at this point, having called the exit system call, that the process might be just completely gone and vanished from the system. And that certainly would have been a plausible way for the Unix architects to have created this mechanism, but they were wiser than that. If you think about what's going on as that child process completes, it does need to signal to the kernel that it's done executing. And once it calls the exit system call, it's no longer going to be scheduled. It's not really going to consume much additional system resources and so forth. But remember that that child process can send a status value back to its parent process. And because the child process might terminate before the parent is even looking for that status value to be available, the kernel hangs on to some vestigial remains of the state of the child until the parent process actually waits for it. Until the parent process waits on the child and retrieves that status information, the child process is going to still be hanging around. It's not going to ever be executed again by the kernel, so it's not really consuming resources in that sense, but there still is an entry for the child process in the kernel's process table, and in order for it to finally be laid to rest, the parent has to wait for it. While it's in this state, the child process is usually called a zombie process. It's still kind of there, but it's not really doing anything. So there's poor, sad, pathetic zombie Tux. When the parent process gets around to invoking this wait call, what's going to happen is that the parent is going to be given that status value from the child, and at that point then the kernel is going to be able to release all the remaining resources, the process table entries and that kind of stuff for the zombie process, and it will never be heard from again. Let's take a look at what that wait call looks like. So here's a definition of a wait system call. This particular variant of it is going to actually cause the calling process to be suspended until some child terminates. Note that we've only been talking about a parent process creating one child process with a fork, but it could in fact create multiple child processes. And when it's getting ready to wait for those processes to be done running, you could wait for a specific one, or you can wait for any of them to complete and just get the first one back. There's various alternatives for doing that. But in this instance, we're going to suspend until some child terminates. And when that child does terminate, this wait function is going to return the process ID of the child that was waited for. And then if you hand in a parameter here that's a pointer to an integer, you can retrieve additional information about the status of that child process. So the reason that it terminated, what its exit status was, and so forth. So that's how the parent can sort of synchronize with the child process when it finally exits. It's also possible, if you aren't writing your parent process code responsibly, that the parent just never actually executes this wait system call. If that's the case, then what happens if the parent itself terminates without ever waiting for the child? Well, you'd think maybe that would mean that the child process would remain a zombie process forever. But what happens is that the parent process, if it goes away, the kernel realizes that there are child processes for which that parent process hadn't waited. And what it does is it sort of reparents those zombie processes on the init process, which I mentioned before. Init process is process ID 1. It's the very first process that the kernel starts up, and every other process in the system is going to have been started by that init process or by one of its children. So it's kind of the great-great-great-grand ancestor of all the other processes in the system, and that's what ends up inheriting the ownership of those child processes whose parents terminated before waiting for the children. And normally what init will do is just go ahead and do a wait and ignore the results. So it cleans up any remaining zombies after their parents have themselves been terminated.